In this presentation, we'll take a look at the ThreadPoolExecutor. If you recall from an earlier demo, we looked at something called the ProcessPoolExecutor, and because they both derive from the Executor class, they are going to behave very similarly. So as a matter of fact, I am going to pretty much start with the same code that we had in the other demo. So I went ahead and pasted that in here. There are going to be a few little differences here and there, but I wanted to demonstrate that they're so closely related that you don't have to change your code all that much when you're using one rather than the other. One big change, however, is take a look at the main execution code here where it checks to see if our module name comes back as main. In other words, we were executed directly by Python. Notice that we have it set up so it prints main execution if it's double underscore main double underscore for the name. And then else, I have a print statement here. Worker thread spawned should never get here. And this is because we're going to use ThreadPoolExecutor, which spawns its threads in the same process that executed them. So we don't, in fact, get multiple versions of this Python module executing at the same time. So we only will get through the code by coming through this main thread of execution. We won't have this else ever run. If we do, that means we've probably done something wrong in our code. Let's go to the top here just so you can see what the differences are. So when we create our executor, instead of being ProcessPoolExecutor, you'll see it's ThreadPoolExecutor. And other than that, it's the same call to submit that we do for power, and we get the same result function call, which allows us to get the result. There is no difference with the multiple futures either. So we can specify the maximum number of workers again, and we can create a list of workers, and then we can append each one of those executor.submit calls to one of the inside the worker list. Okay, and we'll have 4 of them here, and then we can print the results. So these two methods, there's absolutely nothing different. So let's go ahead and run them just to demonstrate it. So we have single future and then multiple futures. Let's run the single future first, and we'll say Python TPE demo.py. You can see it spawns the thread and it prints the results. Really no difference than what we did before. What else do we have? Oh yes, I was going to show you that the multiple futures pretty much executes the same. And let's run this again. You can see we have the same, pretty much the same results we had before. Clearly, if we're using random numbers, we're going to get different actual answers, but we get the same basic execution. However, notice we never print out worker thread spawned. We only ever see main execution. That's because each of the threads is in this same process. So let's go ahead and take a look where things might change. Okay, we have our sleep here, that's fine. That's the first one. We did the many futures with the map. Let's take a look at the as complete here. Okay, this one is going to use the sleep_rand function again, just like we did in the previous example. Let's take a look at sleep_rand. You can see, oh, we're playing with that shared value again. Let's make sure it's in here. Here it is. Shared value is 0. Watch what happens when we run that code. So we're going to run the many futures as complete code, which is going to make use of that shared variable. And let's make sure we have the many futures as completed. Okay, we need to print out our shared value here when this is done. So we can say print shared value is shared value. Let's make sure we indicate that it is a global. Save it. Let's run this again, and hopefully it'll run the many futures as complete code. And now you can see shared value is 10. So what does that mean? That means for each, I'm sliding back up here to the sleep rand function, every time this function completed, it augmented by 1. We spawned 10 threads, therefore shared value is now 10. Remember, when we used instead of the thread pool executor, we used the process pool executor, it was always coming back 0. And that's because each of the modules that was spawned had its own version of shared value, and it never augmented the value. Because, at least it did locally for each of the different processes, but the main process never saw any of those changes. Therefore, it always stayed 0. So if you need to share data between your different threads, ThreadPoolExecutor is the best way to go. However, I am going to warn you about playing with a global variable like this without any kind of protections around it. If you don't have synchronization locks around these global variables, you could have two threads attempting to modify the value at the very same time. Now, with something like just adding 1 to it, it's a relatively atomic process. Typically, it's going to execute very fast, and you don't have to worry about the two threads butting heads on it. However, if it is a longer process, let's say you're updating a list or removing an item from a dictionary or updating an item in a dictionary, which takes more than one single cycle, then you could run into a situation where you have two different threads manipulating the same memory at the same time, and those kinds of results can be unpredictable. It could crash a program, it could just give you bad data. So you have to be very cautious. Now, synchronization is something that we're not going to work on in today's demo because that is something for a whole demo on its own. Okay, but let's take a look at some of the other implications about when you use the thread pool executor as opposed to a process pool executor. I'm going to slide down here just above the main function, and I'm going to paste some code. And the reason I'm pasting it is because you don't need to see me type this. I just need to explain what's going on here. So we create two essentially global variables, A and B, and set them both to none. Then we'll have a function called wait on B, which is essentially going to be one of the runnables or one of the thread functions. And then we'll have another one called wait on A. Now, in wait on B, it references the global B variable. It sleeps for 5 seconds, and then it's going to print the B result. Now, what is B? Well, B is going to be a future. And B is set to be the executor submit wait on A. So B is waiting for the results of essentially this method, which in this method, it looks pretty much the same. We have the global A this time. Don't need to print A. I was just putting some debug statements in here to see if it actually ever got there. So print A, sleep 5 as well, and then print A's results. A's result is the submit for wait on B. I don't know if you're seeing it already in your head what the problem here is. The wait on A is waiting for the results of A. A is spawning off wait on B, which is going to be the B result, which is going to be waiting on A. So B waits on A and A waits on B. What happens is we have something called a deadlock situation where neither can complete now. And you'll probably have to forcibly kill your terminal or your Python process to allow your code to continue. Now, it's actually kind of hard to get into this situation when you're trying to actually do it. However, you may find yourself, without realizing it, we have A waiting on B, B waiting on A. Obviously, it's contrived. But what could happen is you could have multiple threads waiting for some resource to complete. And then that is waiting for yet another resource to complete, which was dependent on the first one. And then you get into the same deadlock situation. Okay? This is something you must avoid at all costs because it will kill your program. So it's actually known as a deadlock situation. So I'm not actually going to execute this method to demonstrate what happens, because all that's going to happen is it's going to kill my Python executable, unless something weird intercedes and allows it to work. But this should, in fact, deadlock the system, in which case I will never see the results. Now, what about future cancellation? Let's say we spawn off many different threads that all do their work, and we need to indicate to them it's time to quit. How can we do that? Well, think about what I'm talking about. Let's say you spawn off about 100 threads, and each one is monitoring a different folder to see if there's any files that are coming in that are changed, etc., but you want to kill the service. So you have to tell these 100 threads nicely to stop doing what they're doing. So how can we go about doing that? Well, this is where we can use signaling, or even better, for right now, we can use a simple global variable similar to what we were doing with remember the shared value? We can do something very similar. So I'm going to create a new variable in here called quit, and I'll set it equal to false. And then I'm going to define a new thread method, or a new worker thread method, that is going to run indefinitely. And I will put that, I can just put it right here. We can keep everything together to some degree. So we'll have this method called run indefinitely. And let's take a look at it. It's similar to our sleep rand function. We accept a thread number, and then we're going to sleep for some value, 1 to 3 seconds. Doesn't really matter. But what does matter here is it's in an infinite loop. Okay, so it's going to say thread is here still, then it's going to sleep. Then before it goes into the next iteration of the loop, what does it do? It checks to see if quit is true. If quit is true, then we're going to indicate it's time to quit. Okay, probably should be nice and indicate it's a global variable, but it's all right. We're fine the way it is right now. And then we can spawn this off in a new method down here. Let's call it def cancel tasks. And cancel tasks will have the quit variable. Okay, we'll put global here. Let's be nice. And then we'll say thread count is equal to 4. Oh, didn't hit the enter key. And then we're going to say with ThreadPoolExecutor, and we'll say thread count as executor. We'll submit all of them using a comprehension. And then we're going to prompt the user to just press enter to quit. And when it does, we're going to say quit equals true now. We want it to quit. And then we'll have, this shouldn't be indented, sorry. We'll print, I'm just going to use these less than, greater than signs again, just to emphasize this is stuff being called from our main thread. So waiting for threads to quit. And I'll put a \n here as well. It's a new line character. And then we'll wait for all of the futures. And I don't know why it keeps indenting here. We'll wait for all the futures to complete, and then we should be done. Okay, so let's go ahead and call cancel tasks. Okay, let's save this. And my terminal is in an interesting state, so let's go ahead and I'm going to trash this kernel, or this terminal. I'll create a new terminal. Okay, Python. Oh, let's clear it first. You don't need to see all that. Python tpe demo.py. So notice here it said thread 0 here, 1, 2, 3 here. Press enter to quit. So this is the problem when you have one terminal being shared by multiple threads, because it said to press enter to quit up here, but it's continuing to print based on what's in the threads. Now when I hit the enter key, it should set quit to true, in which case all of those threads will then signal to quit. So thread 1 is quitting, 2, 3, and 0. And, well, don't worry about shared value is 0. That's an artifact from our previous run. So this is one of the easiest ways to get threads to quit nicely. Another way would be, there's a way to say to cancel it, to signal it should be canceled, but in fact it doesn't really cancel that particular thread. What it does is it prevents any queued threads from getting started. Really, for a thread to quit, you need to use some signaling technique like this. So these are some of the academic examples showing how to use the ThreadPoolExecutor. Now, there are going to be other demos which work with specific tasks to demonstrate how the ThreadPoolExecutor and the ProcessPoolExecutor work when trying to solve a real problem.